Hey guys, it's Megan. We're going to be talking about different models of reinforcement learning, and the first one that I will be doing is DQN, Deep Q Networking. So before we talk about DQN, let's review Q learning. In tabular Q learning, a memory table is full of action value functions from all possible combinations of state and action. So in this example, we have an agent, a knight, and an environment, and a corresponding Q table that would be filled out that represents this environment. Each state in this environment or each square in this grid represents a state. And within the state, for example, this red state right here, it has a corresponding action value function for all the actions within that state. Within this state, as you can see, and within every state in this environment, there are 4 actions, left, right, up, down, and there'll be an action value function that correlates with each action within the state. Like we can look at this blue state right here, and we can see that going up will have an action value function of 0 because going up is out of bounds. And left, right, and up, or left, right, and down will have a action value function, which will be calculated later. So what is the action value function and how can it be calculated? The action value function indicates how good it is for an agent to pick action A while being in state S. The value of taking an action from a state is the total amount of rewards that an agent can collect from now to the end by taking a specific action. The equation for the action value function is given below. The Q value, or the action value function, for that state given that action is equal to the expected discounted cumulative reward given that state and that action. So let's ignore discounted for now. We'll talk about the discounted rate later and see that the Q value, or the action value function, and in some ways is the summation of the rewards at each step into the end or until the agent reached terminal state. We can look at our last example of our knight here and our terminal state down here and say, for example, the knight in the initial state, each state in our environment has a correlating reward, and say the knight or agent in our initial state takes action right and follows this path to the terminal state. The action value function for the initial state given action right is equal to the accumulation of the rewards. So R1 plus R2 plus R3. And our goal in a machine learning algorithm is to maximize the expected return. So this is a completed Q table with correlating action value functions after 1,000 episodes. And say if we started at this initial state at the upper left corner, we can see that action right in each state is favored because it leads to the maximum rewards in this environment. What's important to also note that the lowest reward in this environment, this -1, is surrounded by action value functions that are quite low compared to everything else in our environment, and that just shows that the algorithm is trying to lead the agent in taking actions that do not go into these states in order to maximize reward. Let's talk about the discount rate. The discount rate is typically talked about in the context of reward. So the reward function equation is given below. RT is equal to R subscript T plus 1 plus gamma times R subscript T plus 2, etc., etc. If the gammas or the discount rate was not present in this equation, we can see that RT just increases as t goes to infinity. We would like the reward to be a single value. So having the gamma present, and present in the sense that it increases exponentially at each term, prevents the cumulative reward from going to infinity and allows convergence towards a single value. The gamma or the discount rate ranges from 0 to 1. 0 gravitates towards more immediate reward. Say gamma was equal to 0, then these terms just cancel out, equal to 0, and RT is equal to RT plus 1, the immediate reward. If gamma was from 0 to 1, it's just future-oriented reward. So here's just a nice visual of an action value function. So the action value function goes to a new state, and in that new state, each action is given a new action value function. So after the Q table has been initialized by action value functions, it will update itself via the Bellman equation. And the equation is given below. new action value function for that state and that action is equal to the current action value function plus the learning rate multiplied by the reward for taking that action at that state plus the discount rate. Multiply that by the maximum expected future reward given that new state and all possible actions at that state minus the current action value function. It's pretty hefty, and I'll try my best. But we can think of it like we have a Q table that is initialized by action value functions, and say each action value function is 0 because this is the beginning of our runs. So the current action value function, say we decide to go, and we're in state 1 and we go write this action right here, is 0, so this is 0, plus the learning rate, which we'll talk about in the next slide. The change in the action value function. So the learning rate controls the differences between the previous and the new Q value. It is a parameter that adjusts the weights of our network. So let's look at an example of a Q table being updated by the Bellman equation. We have an environment of a mouse, and the rewards correlate with the amount of cheese in that state. So this is a +1 reward, this is a +2, and this is a +4. And this is our Q table initialized by action value functions of 0 because this is probably the beginning of the training. The Bellman equation is given below. So the new action value function of being in state start going action right is equal to the current action value function in state start going action right plus the learning rate multiplied by the change in the action value function in state start going action right. So to find out this term right here, remember is reward given in that state, in that action, multiplied by the discount rate, plus the discount rate multiplied by the maximum expected reward in the new state and all possible actions in that new state minus the current action value function. So the reward going in this state going right is 1 because of the cheese, so that's 1, plus the discount rate, which seems to be 0.9 and which we know is future oriented, multiplied by the max of the action value function of the possible actions in that new state. And the possible actions in that new state is right, left, and down. And we know those action value functions is all equal to 0, as seen in our Q table, minus the current action value function, which is also just 0. So we have 1 from the cheese, the 0.9 from the discounted rate, multiplied by the 0 because all the actions in that new state is 0, minus the current action value function, which is also 0, and that all equals to 1. And so we plug the 1 back into this equation here. And so like I said again, the action value function initially was 0, plus the learning rate, which is 0.1 multiplied by 1, and the new action value function in that state, in that action, is 0.1. So here's a summary of the Q learning algorithm. You initialize a Q table, choose an action A, perform action, measure the reward, and update the Q using the Bellman equation. And that's essentially what's being said on the right side, except more technical terms. You initialize action value function given all the states and all the action. Say for example 0. You initialize a state and you choose an action within that state that's most optimal. You take that action and you observe the rewards in that new state. You update the action value function in that state given that action using the Bellman equation, and then you go into a new state and you repeat each step for each episode until S is terminal or until you reach the end, and you repeat for each episode. Although the tabular Q learning method is great for looking at action value functions or value functions, it has limitations when it comes to big state space environments. Think of games that have more complex inputs and a lot more than just taking actions up, down, left, or right. So DQN deep Q networking expands upon tabular Q learning and takes large sets of observations in each iteration. The biggest difference between tabular Q learning and DQN is the introduction of a neural network to take states as the inputs and predict action value functions for every action in that action space. Like shown in this diagram here, tabular Q learning takes state and action to output action value functions. In DQN, it just takes the state into a neural network to output action value functions for every action in that action space. So let's try to briefly talk about the fundamentals of a neural network. Say the neural network takes inputs, say the state, and predicts action value functions. And then it interacts with the environment and takes the outputs as a new set of inputs to update the internal state. Using the inputs and the predicted outputs as well as the true outputs from the environment, it updates the internal state. Now when the neural network runs through the environment once again and gets new inputs, it outputs and predicts from using this updated internal state. So here is like 7 general steps of a neural network. Firstly, model initialization. The most popular way is random in the beginning, where the model kind of just randomly runs through an environment, gets inputs, and predicts action value functions. Next is forward propagation, where these predicted action value functions are checked, and we run through the environment and get actual action value functions. Then a loss function is calculated, where we look at the differences between the predicted and the actual. The loss function acts as a performance metric on how well the neural network manages to reach its goal of generating outputs as close as possible to the desired values. Then we differentiate this loss function, and we try to find where the rate of change of the loss function is 0. We backpropagate, we go back, and we look at our inputs, and we recalculate the predicted action value functions. Using those changes, we update the weights of our neural network, and we iterate until it converges. In a neural network, after each iteration, the gradient descent force updates the weights towards less and less global loss functions. So the neural network is trying to minimize the loss function, minimize the differences between the predicted action value function and the actual action value function. Here is another pretty picture of a neural network. And so we can start in step 1, random initialization, where we randomly assign weights to our models to predict the action value functions. We forward propagate, step 2. We interact with the environment, we get inputs, and we get the actual action value functions. So then, since we have the desired output from our weights and models from our random initialization and the actual outputs from forward propagation, we can figure out and calculate the loss function. From there, we can find the derivative of the loss function where the rate of change of the loss function is 0. And from the derivatives of the error, we have gradients. And then we backpropagate and we recalculate, and we update the weights of our model, and we iterate until convergence, meaning we iterate until the weights of each iteration is a single value versus like a weight being this, and different iterations. We just want the weight to be one single value, and that's convergence. So let's talk about the loss function, because the loss function is pretty integral and critical to the functionality of a neural network. A loss function is a performance metric on how well the neural network manages to reach its goal of generating outputs as close as possible to the desired value. A neural network tries to update its weights to reduce this loss function and reduce error in between the predicted and the actual outputs. So there's multiple ways to calculate loss, but in general, loss is equal to the predicted minus actual to the power of 2. The reason why the power of 2 is present in this equation is because we want to differentiate the difference between a small loss and a large loss. Say, for example, the loss in one iteration is 2, and another iteration, the loss is 10. Taking the power, the loss is now 4, and the loss is now 100. See here, we can definitely tell the difference between a big loss and a small loss, because the difference is this 96, while the differences before was just 8. Now let's talk about gradient descent, because that's typically how we talk about loss functions in terms of gradient descent. Gradient descent is an optimization algorithm used to minimize some function by iteratively moving in the direction of the steepest descent as defined by the negative of that gradient. In machine learning, we use gradient descent to update the parameters or weights of our model. We can look at this example here of a mountain. So our goal is to move from the mountain in the top right corner, the high cost, to the dark blue seas of the bottom left, the low cost. The arrows represent the direction of the steepest descent, the negative gradient. From any given point, the direction that decreases the cost function as quickly as possible. So in the differentiation process of our neural network, we take a derivative of the loss function. We are essentially trying to find the rate of change of our loss function and determine how much the total error will change if we change the internal weight of the neural network to with a certain degree or with a certain small value. We really care about the rate at which the error changes relative to the changes of the weight. Say, for example, we have a weight here, and the derivative of the loss function is negative. And then we change the weight by a factor of 0.001. Now, the derivative of the loss function of this new weight is positive. What we're trying to do here is we're trying to find a derivative of 0, meaning that the rate of change of the loss function is 0. What we want here. And say like we change the weight by this factor, 0.001, and we find out that the rate of change of the error is now 0.006. And now we can have like this kind of conversion factor where we say like if we change the rate by this number, then we know that the rate of change of the error is this number, which is important to find this 0 derivative here. So as a result of the neural network and its kind of flexible learning algorithm, DQN is able to master a diverse range of environments. DeepMind has able to make DQN algorithms master 49 game scenarios, for example. And so a basic overview of the DQN code and algorithm is, firstly, it initializes action value functions with some initial approximations. It interacts with the environment and obtains the total of state, action, reward, and the next state. It calculates the loss. It updates action value functions using gradient descent by minimizing the loss with respect to the model parameters or the weights, and it repeats step 2 until it converges, until the weights converge to a single number. So if we go back to talking about learning rate, which we previously mentioned was a way to differentiate the original action value function and the change in action value functions. Now the learning rate, in addition to that, is the size of the steps we take in gradient descent. So the new weight is equal to the existing weight minus the learning rate times the gradient. And so we can see here that if the alpha or the learning rate is small, the gradient descent can be slow, but the convergence is quite accurate. If the alpha or the learning rate is large, the gradient descent can overshoot the minimum and it may fail to converge. So let's look at some applications of DQN. An example is Doom. So here is like an overview of DQN algorithm being used in Doom. Firstly, we take the image and turn it into a grayscale image and crop the necessary image parts. Then we apply convolution filters and full connected layers with the output layers. And then thirdly, we give the image we call states, calculate the action value functions, find the error, and back propagate. And then we repeat. So the DQN takes a stack of 4 frames as an input. We do so because if we just look at a single frame, we can't really indicate much from that single frame. So if we take 4 or multiple frames, we can indicate direction. We can look at here the example of Pong. See, if we look at one image, you can't really know what's going on. But if you look at 3, we can see that the agent is moving towards the right. So what is a convolution layer? A convolution layer is essentially a neural network that are used primarily to classify images and perform object recognition within the scenes. So these algorithms in the convolution neural network can identify faces, individuals, street signs, tumors, etc. It takes visual data and analyzes it. Within each convolution layer, we'll use an ELU, an exponential linear unit, as an activation function. So an activation function defines the outputs of that node or neuron given an input or set of inputs. So it's essentially a function, right? You have an input, you put the function input into a function, and it has an output. There's multiple types of activation functions. There's linear, where it's a straight line function where activation is proportional to the inputs. And then there's exponential linear unit, a function that tends to converge cost to zero faster and produce more accurate results. So here are some other aspects of DQN, skipping frames, which is similar to the stacked frame, experience replay, fixed target network, and a reward clipping. The experience replay functionality of a DQN uses something called replay buffer, where every experience, where we have data that is current state, current action, reward, next state in our memory, and we take that and we store it into a replay buffer, which then stores it and samples it into batches of experience. We do so that we avoid forgetting previous experiences, as well as reduces correlation between experiences. Say, for example, we had a game where monsters either popped out from the right or from the left, and our job as an agent is to have a gun either on the right to the left to shoot these monsters. Say, for example, based off experiences, that the monsters appear 70% of the time from the right, and so the agent begins to favor the right gun. And this isn't really what we want. So the correlation that the algorithm is associating is like right gun equals terminal end. What we want the agent to learn is monster equals end, not right equals end, essentially. So another interesting and integral critical part of the DQN algorithm is something called a fixed target networking. Essentially, you have to remember that DQN is a reinforcement learning algorithm. And so actual data isn't given to the algorithm because it's not supervised learning. So this actual data is actually calculations done by another neural network. This secondary neural network is maintained and assign the actual network weights to the target weights. And so the formula for the actual data is given in box 1, which is reward plus the maximum action value function of all the actions in a new given state. And so the reason that we have a secondary neural network is to store the actual neural network from the other neural network that's constantly changing, updates its weight. So we store the actual weights in the secondary neural network. Additionally, it's also just to keep stability. So we update this secondary neural network every so often, not every single time. And so that way, if the first neural network, which updates every single iteration, finds data or experiences that are biased or like outliers, the secondary neural network has and stores the previous weights that aren't affected so much by these outliers. So it just keeps the stability of the algorithm intact. Lastly, in order to account for diverse environments and play like 49 games like DeepMind promoted, the rewards and penalties are normalized uniformly across all settings of environments. So here's a summary of the DQN algorithm using the replay buffer. Firstly, we initialize a replay memory D, initialize action value function Q with random weights, observe the initial state S. We select an action, we carry out that action, we observe the rewards and the new state, and then we store all this data in a replay memory. Then we go back and we sample these random transitions, looking at the past state, the past actions, the rewards, and the next state afterwards from this replay memory. We calculate the target for each mini batch transaction. We calculate the target for each memory. If the new state is terminal, then the target is equal to the reward. Otherwise, the target is equal to the reward plus the maximum action value functions of all the actions in the new given state. And then we train the neural network using the loss function, the target, which we determined previously, minus the action value function squared. And then we update to a new state. And then we repeat all this until the episode is terminated. So in a quick summary of what we learned in this video, we talked about tabular Q learning, which is a table that represents our environment full of action value functions, and these action value functions represent how good that action, if taken, is in that state. And then we talked about how the Bellman equation is used to update the Q table in each iteration. Then we talked about the difference between tabular Q learning and DQN, the main difference being an introduction of a neural network. And a neural network has about 7 general functionalities and features. Has model initialization, where we predict some values. We have forward propagation, where we check those values and get actual values. We have the loss functions. We have differentialization. We have backwards propagation, and then we change the weights, and then we iterate until convergence. And then we talked about the specific features and algorithms inside a DQN, where we have stacked frames, we have skipping frames, which is kind of the same thing, and then we have something called a fixed target network, which is a separate neural network that stores the actual action value functions. We have the replay buffer that stores the memory of experiences in a batch folder, and then we have reward clipping, which is a normalization and uniformity of rewards and penalties across all different environments. And yeah, that's what we talked about in this video. So here are my sources, and thank you for listening.